start recording on my computer. So do you see a notification of recording on? Okay.
Yeah.
So maybe I will just try to introduce our speaker and then we will start the seminar. So thank you everyone for turning up in a relatively unusual time in the evening, but still nonetheless. So we are extremely glad to have Dr. Anindita Maiti, who is our speaker this evening. So Dr. Anindita Maiti is a postdoctoral fellow at Perimeter Institute since September last year. Before that, she was a postdoc fellow at Harvard, working on the theory of deep learning during May to August of 2023. Anindita received her PhD in theoretical high-energy physics at Northeastern University and NSF IAIFI, supervised by Professor James Halverson in May 2023. Her research focus includes correspondences between neural networks and field theories, formulating field theories via foundations of machine learning, and lastly, theory of ML via field theory. So we are extremely glad to host Anindita, and let's see how much we can learn from this seminar. So Anindita, the floor is yours and you can now start.
Thank you, Sanmay, for both the invitation and the very nice introduction. And thank you to everybody in the audience. People in the audience might not have heard what I was telling Sanmay a while back that my undergraduate was in IIT Bombay, a sister IIT to IIT Kanpur. So I was very excited when I got this invitation to present on the work of last 7 years to the audience at IIT Kanpur. So without further ado, because we are short on time, let's get going. So although it's a technical seminar, I would appreciate discussions in the interest of time. It would be good if we can take questions after I get to finish parts of a section. So there are 4 sections in my talk, but if there are pressing questions that the audience simply cannot suppress, please feel free to interrupt and ask. But if you can hold the question until I finish the section, I would appreciate that as well. So I'm supposed to give an introduction to this particular topic called neural network field theory. This is based on 3 existing papers with my PhD advisor and many amazing collaborators. I forgot to include one of my collaborators probably anyway, and one of our ongoing works that includes some aspects of supersymmetry. I won't get to talk much about supersymmetry. For the most of my talk, it would be based on setting up a correspondence between neural networks and statistical field theories, with giving a clue on how we want to explore a correspondence between neural networks and quantum field theories. And I'll stick myself to scalar field theories and then Grassmann valued and fermionic field theories on Euclidean background for today's talk. So let me start with defining this particular jargon that I threw in. Relatively new thing. I'm sure most of you have heard about neural network architectures, which act as the backbones of machine learning techniques. Machine learning has been the revolution on computer science and artificial intelligence over the last 10-ish years. So I'd be surprised if audience has not seen this term floating here and there. But the neural network and field theory together generally do not appear in the literature of theoretical physics so much as of now. And that's because these belong to different fields. This is from theoretical physics. At best, you will see them in high energy physics and condensed matter physics, and then neural network is a terminology from computer science. If you have familiarity with neuroscience, you will see them see neural networks appear there as well. But the point here is that although these 2 subfields seemingly are very different, these 2 topics within these subfields have mathematical correspondences. In fact, the mathematical correspondences are so nice that we can leverage them to use neural network architectures, a foundational part of machine learning, to formulate some questions in field theory. And we can also do the reverse. We can take some techniques from field theory to formulate some questions in the theory of machine learning. So this term in a nutshell refers to a field theory defined by output ensembles of an initialized neural network architecture. This word is the key. So at a later point, I will also mention that it is possible to have neural network field theories during training algorithms, in the sense that when the training updates neural network parameters, there is still a neural network field theory that you can define. But primarily, our work focused on investigating neural network field theories when we have an initialized architecture. That is, you have fixed the details of the architecture and you have not fixed any details of the learning algorithm. That can be whatever. But the point is, we will leverage this duality or correspondence that I just mentioned to represent field theories by initialized neural network architectures. And such field theories are called neural network field theories. And in principle, they can contain all known field theories, both statistical field theories as well as quantum field theories. So why do we want to get there? It sounds pretty cool, I'm sure, but practically, what does it offer us that machine learning already does not offer? So the answer to that is here. We all are, I believe, those of you who are familiar with machine learning for high energy physics, not all, those of you who have looked into machine learning for high energy physics have seen various nice learning algorithms that help simulate quantum field theories on lattice. And those nice algorithms generally take a known neural network architecture. By known, I mean something that the machine learning community has given us. There are very nice neural network architectures, lots of them out in the community. In the machine learning community, generally we take some of them and then we think very cleverly how to train them. The idea here is that we train those neural network architectures given by machine learning community in a clever manner to approximately match our target field distribution or a field configuration. It's generally a function or a functional distribution that we try to match. But the point of training is when you are just taking some neural network architecture that the machine learning community handed you over on a plate, there is no inherent notion of what the neural network output or different components of the neural network means from a physics point of view. So some interpretation is required if we want to have a very nice simulation toolbox in high energy physics coming from the machine learning side. And that interpretability should be such that we can cut down on unpredictable errors and biases that machine learning generally offers. Just to give an example, all of you have heard of these large language model hallucinations. Someday in the future, people will find a way to implement large language models for some simulations in high energy physics, which does not have to be quantum field theory. But if we do not understand how the large language model outputs would be related to that objective, the very physics objective, then it would be very hard to cut down on possible hallucinations and biases. So as a physicist, you would want a way to guarantee that the neural network outputs have some semblance with a target. In my case, the target is a field distribution or a field configuration. You want to ensure that you have some kind of a theoretical guarantee, something postulating that the neural network output or some configurations or functions made out of the output can represent something entirely physical. So with that kind of a postulate, then you can tune any kind of errors or any kind of biases that arise when you train or even when you do not train. So it gives you some kind of a better understanding of what machine learning does as a simulation toolbox for field theory here. The other thing is, in general, machine learning techniques for quantum field theory require a lot of compute resources, especially when you need to train them. And in most cases, you need to train them. And neural network field theory correspondence is focused on initialization. Training offers something extra that I will briefly touch, but because it is based on initialization, one can cut down the compute resources. And it is actually important because if you look at the new models that are coming out in the machine learning community, those are larger and larger and they take up more and more compute resources. In fact, maybe a few years from now, there will be very few models that will be useful without a GPU. And definitely, as a physicist, you want to make sure that you don't have to buy many GPUs just because you want to do some nice calculations. So it is useful to know without much compute resources what's there, what can we do to still being able to simulate some field theoretical aspects. So the answer, neural network field theory correspondence, not the full answer, a partial answer to these questions about interpretability, robustness, and uncertainties is that if we can start at initialization and if we can show how the neural network architectures are directly representing field theories without involving training algorithms, and if we can do that in a meaningful way such that the outputs have some physics-based nice interpretations by some postulates or theorems, then at least we will know that we are one step closer to a sensible, scientifically interpretable, and scientifically tractable in terms of errors simulation method. So this neural network field theory, in fact, offers you methods via theorems to impose some kind of a symmetry in the target field theory that you are simulating at initialization. It also lets you engineer field interactions at initialization. So when I say engineer, what you're getting is an analytical description of a neural network architecture on pen and paper that is supposed to give you a target field theory. So by analytical representation, I mean that when you think about neural network and machine learning, what you think is a sort of a black box, an architecture that you take generally from the internet, then you train it. Generally, you can use scale divergence or something. But at the end of the training, you are getting a neural network architecture that's giving you the target answer, but it is essentially a bunch of numbers. The neural network is made of a bunch of numbers. You cannot just take all those bunch of numbers, the updated parameters, and try to interpret them. That generally does not go well. Versus when I say an analytical description of the target neural network, what I mean is you can basically define the neural network architecture as a statistical system. You can define what various hyperparameters would be, what the parameter distributions would be. And then once you have that solution, you can generate that neural network on your computer. You can generate the outputs as many times as you want. So that's the power of neural network field theory that usual machine learning algorithms, machine learning modules do not offer you. Here is the talk outline. I'll go for the introduction to NNFT, then I'll take questions based on what I'm covering so far. And then there are three more topics. One is starting from a generic neural network architecture to inferring what is the action associated with a field theory that it represents. And then an engineering part where you have a target action. And from the action, you engineer an analytical description of the architecture that represents this field theory. And lastly, this is a work in progress, Grassmann field theory. Introduction and create the Dirac example, and I'm not gonna cover supersymmetry. And here, I don't know how much time I will have to cover this one, but I'm happy to discuss this in the discussion after the talk. So first, the intro. If you guys look up a generic neural network architecture, all right, let me pause at this step and take questions before I go on with the introduction.
Anyone have questions, then they can raise their hands, probably. I don't see any, so please.
Yeah, I assume that there's no question at this point. All right. So this is a generic neural network architecture that I generated this using particular software online, and you can also find many ways to get a neural network architecture. So this is just a diagrammatic representation of what is known as a fully connected feed-forward network. People call it FCN. And there are many nodes. There are connections in between the nodes. And in this example I have given, the nodes of each of the layers are kind of separate. They are interconnected only to adjacent layers, but not between themselves. Now, there are nodes that do not have any connections on one side. They are kind of free on one side. And these are the input nodes. That's where the data to the neural network comes in. That's the data user gives. And then there are nodes that give you out something that's summed up at the end of the day to get the output. And this layer, right before the summing happens, is generally referred as the last hidden layer in the machine learning community. I have used the notation I for input nodes and H for the last hidden layer nodes. H1 to Hn means that there are n nodes in the last hidden layer, and the outputs of the last hidden layers are summed up to give the final output O1. Schematically, for the rest of my talk, I will represent them using this kind of a diagram where the actual architecture is hidden between this part. It can have many hidden layers. What this represents is just the final hidden layer, and these are the neurons of the final hidden layer. Nodes are neurons with the connections. So rather, neurons are nodes with the connections. So this is a function of the original inputs that come in, and so is this. Each of them are functions of the original inputs that come in. And then all of them are summed up to give you the outputs. And this notation just means that the output has two components. So output is here a vector. Anyway, moving forward, the inputs are denoted as x, similar to the points on a Euclidean space. And then the outputs are normalized sums over all these neurons in the hidden layers. Here is the normalization factor. Now, the neural network field theory correspondence sets up the inputs as equivalent to points on Euclidean space, or if you can show that this neural network is dual to a quantum field theory, then the inputs would be points equivalent to, points on the Minkowskian space, and the outputs are fields evaluated on these particular points you have chosen from the Euclidean space. So the output itself is a function, and you can see that this is a continuous function because x is continuous. But for practical purpose, when you are generating neural network outputs, you cannot actually generate a neural network output that is a continuous function. Rather, it becomes a collection of numbers, and those numbers represent the field. Actually, those numbers represent a single field configuration associated with the dual field theory of this architecture. But those are evaluated on this choice of inputs. That's essentially the point. So if you have a collection of 10 numbers as your inputs, and suppose you are getting scalar outputs at the end, and each of these phi of x for each of the 10 values of x would represent the field phi evaluated on that particular point xi. The crux of NNFT is that an ensemble of the outputs of a neural network architecture that's not evolving with time, that represents a statistical distribution over the outputs. Right now, I'm mentioning just initialization, but even during training, you can take a snapshot during a training step and get an ensemble of the neural network outputs at that particular training step. And then that output ensemble would also correspond to a functional distribution or a statistical distribution over the outputs. In path integral formalism, field theories are equivalent to functional distributions. So this is the similarity. You have got this nice architecture, which is giving you a bunch of numbers that are actually associated with the function phi. And ensemble of phi is equivalent to a statistical distribution in the limit when the number of outputs in the ensemble is asymptotically large, in that limit. And then bringing in this path integral formalism, you can make this connection that this output ensemble asymptotically represents a field theory when the number of outputs in the ensemble is asymptotically large. So the neural network field theory would be given in terms of a partition function, an action, and a measure in that particular limit when you have a very large output ensemble.
I'm sorry, I have a question.
Yeah.
Just clarification. So in the previous picture, should I think of O1 and O2 as two different values of phi of x for the same x? For example,
Yeah, that's correct. That's the notion here. This is x1, this is x2, and this is phi of x1, and this is phi of x2. I didn't have a better diagrammatic representation at this stage, so this is how I'm representing, but you're absolutely correct.
Oh, so O2 is like phi of x2. It's not like, I see. Okay,
Yeah,
thank you.
it is phi of x2. So O1 and O2 are the output phi evaluated at respectively at I1 and I2.
Thanks.
Now coming back here, there's output ensembles that represent field theories. They will have field interactions in some cases. And that case is determined by the some asymptotic limits in the architecture. So the origin of field interactions here happens to be central limit theorem. This is because neural network architectures are statistical systems. And in this particular statistical system, central limit theorem governs whether you are going to get a free distribution over the outputs or whether you are going to get an interacting distribution over the outputs. It can be easy to see from here if you have some familiarity with statistics. So if you choose this n to be infinitely large, and if you choose the parameters to be identically and independently distributed, then these neurons, which are functions of both the inputs and the parameters, they behave as IID, random IID in the sense of this, IID random variables. Actually, they behave as IID random valued functions. So you are summing over n number of IID random valued functions, and if n goes to infinity, you are summing over an infinite number of IID random valued functions. Then such a sum is a draw from a Gaussian or a free distribution. There would be nothing but quadratic term. So that's the way we get a free field theory out of a neural network architecture. And then if we violate these constraints for CLT, central limit theorem, and we can do this by tuning some aspects of the architecture, we can choose finite width in this hidden layer or the previous hidden layers, all such assumptions work. Or we can choose the constraints on the parameters to be non-IID. We can choose dissimilar parameters or correlated, statistically correlated parameter distributions. So this is something we can choose at initialization. This is in our power. We can initialize the architecture however we want, and that choice will give us a pre-distribution over the outputs or an interacting distribution over the outputs. So this is what I mean by parametric tuning. We can break CLT by a large amount by choosing an architecture with really small weight in the hidden layers or highly statistically correlated parameter distributions over all of the nodes. We can choose those, and that would violate CLT by a large amount. And such large breaking of CLT will correspond to a non-perturbative NNFT. So different initialization corresponds to different interacting field theories, but the crux is this is not actually, surprisingly, not a one-to-one map between neural networks and field theories. For example, you will have different free scalar field theories coming from different infinite width NNs initialized with IID parameter distributions, but we have seen that there are more than one choices for activation functions that gives the same free scalar field theory action. And same for interacting field theories when you violate the central limit theorem. Now, one quick point here is that training, is that a question? Training breaks IID assumptions because training generally correlates the neural network parameters as it updates everything in correspondence with, by that I mean in response to the training objective, as it keeps updating the parameters. Even if you start with this architecture with IID parameter distributions and infinite width, with training, you will gather, in general, you will gather more and more statistical correlation among the parameters, and that would induce a flow from a free scalar field theory to an interacting scalar field theory. So far, this description is only for neural network outputs that are scalar valued. Hence, anytime I'm saying field theory in this context, you have to assume that those are scalar field theories. Now, here are lots of related works, and they can be categorized. There is the usual machine learning for field theories on lattice, which is also very successful, but this does not equip the neural network outputs with any kind of physics-based interpretability. So if any architecture malfunctions and have large bias or hallucinations, you are done. And then there are also correspondence between learning dynamics and inverse RG flows, information theoretic RG flows in high energy physics. We recently connected one of those schemes with neural network field theory. I don't talk about that paper here, but that's also one of the ways to understand machine learning from a fundamental physics point of view. There is the topic that I'm speaking about, which is the correspondence between initialized neural networks and field theory without involving any kind of learning algorithm. And then there are other few things. This is purely theory of ML, often involving statistical field theory methods. Now coming here, so the nutshell of what I just spoke about is that the central limit theorem is the origin of interactions. If you validate central limit theorem, then you get interactions turn up in response to the amount of violation. And the way you validate central limit theorem is in the architecture space. You take the architecture, you take the black box, you determine at initialization how much cell do you want to validate by your choice of weight or parameter distributions. And in turn, you know that the interaction strengths collectively would increase or decrease in the dual field theory side. So to summarize, there is a duality. Each of the neural network architectures out there, and by each, I mean, even if you vary, say you take convolutional neural networks, but you keep varying the activation functions, you keep adding layers, you keep adding new parameters on these new layers, new nodes, each of them have a corresponding field theory dual. And in general, those field theory duals should be different, but as I said, it's not a one-to-one map. And the question is, how useful is this for field theory? Can we find out a method to infer the field actions associated with each of the architectures? Can we even go reverse? Can we take an action and then can we define what the architecture should be so that it can represent this action in a meaningful way without involving learning? That is the summary of NNFT. I have not answered those questions, but the summary of NNFT poses those questions, which I will answer going forward. So another thing, I have talked about field theories on Euclidean space so far, but for high energy physics, at the end of the day, we need to have some kind of a correspondence between neural networks and quantum field theories. So here is the subtlety. We all know that not all statistical field theories can have analytic continuation to Minkowskian background. And that actually is true even here. In fact, if all the correlation functions of the neural network field theory, which are equivalent to the statistical moments of the in and output ensembles, if all of them satisfy this criteria, Osterwalder-Schroeder axioms, then this dual field theory has analytic continuation to the Lorentzian background, and then the architecture corresponding to this field theory actually has a correspondence to a quantum field theory. Because although this architecture has a field theory dual, which is on Euclidean space, that theory can be connected to a theory on the on the Lorentzian background, and this connects the architecture directly also to the theory on the Lorentzian background. So the way people will then take advantage of this NNFT correspondence is that whatever you want to compute in the field theory would have to be first computed for the field theory on the Euclidean space. Then you take the advantage of the Weiss axioms and analytically continue the answers to the Lorentzian background. All right, I'll take questions on this part and then I will go ahead with the rest of the talk.
Right. I have a couple of questions, but if anyone else have question, please raise your hands and I will try to unmute you.
I see a question from Jody.
Yeah.
Hi. Can you hear me?
Yes.
Mhm.
Yes. So when you define this partition function, can you go back to the slide? Yeah. So here, when you define this action, do you say that this action and the action differs by the total derivatives? They are basically, you're treating them to be equivalent?
That is a good question. You mean that if
The reason
two
actually I wanted to know that the free field theory that you are defining,
yeah.
are you defining in a manifold without boundary or with boundary? That is the reason
Oh,
actually
that's a very good question. So we are defining this on a manifold without boundary.
okay.
And
So then
in
basically you
general,
don't. Okay. Yeah.
right, because if you want to have a derivative term, that would be a different architecture, because we tried to get
Yes.
derivative terms and then we realized like CNNs have some kind of a
Mhm.
convolutions afterwards. You also need to
Yeah.
have some kind of a convolution afterwards, which gives you derivative
Yeah.
terms. Because at the end of the day, the output phi would have to have some structure or some kind of a layer
Yes.
imposed on output phi will have to give you some structure so that the output ensemble will pick up that derivative term. I can talk about
Yeah.
this in more details going forward.
Okay. Okay. Thank you.
Okay, Anindita, I had a question. Like you
Sure.
told us how to construct a general representation of a field using fully connected network, let's say phi. Now, if I want to write down a composite operator, something like phi cube or phi square at a local point x, can I just repeat the same neural network 4 times, or I need to define a new neural network to map a composite operator at the same spacetime point x?
That's a very good question, and I believe I have the answer for you at the end of my third section.
Okay.
So let me get there, and if it is not clear, I'm happy to discuss you even after time.
And another one, like the prescription you gave is just pretty generic. Like you give an input X and you have an output phi X, and phi is modeled by this neural network layer. And now, how do you ensure it's a scalar field? Like, how do you ensure if I take some general space-time transformation on X, the output remains unchanged?
I'll answer the two questions. The first answer is actually pretty straightforward. Here, you need to make sure that the output of the neural network architecture, which happens to include matrix multiplications and matrix additions, gets proper tensor index contraction and gives you something scalar. So basically, it's something you have to impose on the architecture. In comparison, if I go to the Grassmannian case, let's go there very quickly. Here, I hope this is visible. So in the Grassmann neural network field theory, in fact, the outputs themselves have a Grassmannian nature, and they do have indices. They have an index in a Grassmann space, and that index in the Grassmann space is this. So basically, this would also have to arise from the matrix multiplications and additions between the weights bias neurons post-activations. So what I'm not showing right now is how you generate the neural network output from the architecture itself in the architecture space, in the sense how you get it in terms of the weights, biases, and activation functions. This is a detail I have skipped in interest of time. But if you look into that, I don't have much to show except this. So I have set bias off. This is the last layer weights, and this is the last layer neuron functions. In fact, these are also called post-activation in the machine learning community. And the way I have defined the outputs is such that you are contracting one of the indices. So in this manner, you have to ensure that sometimes you have scalar output versus sometimes you are going to get a vector output, or you are going to get a Grassmann output, or an output that's a mixture of scalar and Grassmanns. What is the second question?
So I was interested in like how do you write down composite operators?
Oh yeah, that I will answer that, but
okay. You can do it later.
all right.
Okay.
Thank you.
Thank you.
Then let me get started with. All right, another question from Jada.
I think Joydeep has one more question.
Sure. Yeah, please feel free to ask.
So the thing is basically, as Sanjay was asking about the addition of the composite operators, I was wondering that because when you add those composite operators, so then your action may have some kind of a redundancy, like field redefinitions and so on. So
Sorry,
when
what
you
kind of redundancy?
field redefinitions, so you can redefine your field and you get back your S matrix to be the same. Your action looks different, but two actions are related to each other by redefinition of the fields, such that your S matrix.
I see what you mean, but it's a little different in case of neural network field theory. We can discuss that once we get there. Do you mind asking the question then?
No, it's fine.
Thanks.
Okay. Thanks.
So let me get started with the next topic. Given the nature of the questions, I think I will keep this section short. So this is a section about how to generate a library of field theories out of the collection of neural network architectures we have got already from the machine learning community. So it's a one-directional arrow right now from NN architectures to actions. And to that end, let me represent a duality. So there is this architecture space where you do not care anything about field theories, and you just deal with the weights, biases, activation functions, depth, hidden layer, and all these details of the architecture. And then there is a field space in which the neural network is a field theory generator. And in that case, the outputs are basically field configurations evaluated on the input points. And here, let me start with the simplest observable one can think of, which is the correlation function of the neural network field theory. These are equivalent to the statistical moments of the neural network outputs. The way you compute this is that, in fact, if you have an ensemble of outputs, which can be true at initialization or during training, you essentially compute the ensembled average over the product of the outputs. So this is the ensembled average. And there is a analytically tractable method to also compute that. If you know all the parameter distributions, which is only possible at initialization and not through training, not during the steps of training when the parameters keep updating. So if you know the parameter distributions, then you can compute the correlation function of the NNFT as this integration here. So this may or may not always be integrable. That's also a thing. But nonetheless, you can always compute them as ensemble averages. And if the number of outputs in the ensembles are asymptotically large, like for practical purpose, it should be between 1,000 to 10,000. In that case, this ensemble average statistical moment is a very good approximation of the correlation function of the field theory. So this is an easy way to compute the correlation function of the field theory, even if you do not know what the full action is. Now, going into some details, I'll keep this short. There is a technical way to see how we can infer the information of the action from the information in the neural network architecture. And this happens because the output can be seen as a draw from a field theory in the field space, or it becomes just a mathematical function, which is a sum over a bunch of random valued functions. For this purpose, here xi is a random variable, not a random valued function, but the technique I'm showing can be promoted to the case when these xi's are random valued functions. So we start from this dual nature of the output, and then the partition function of the NNFT can be expressed as expectation value over the weights and biases of the parameters. So this is, in fact, expectation value over the architecture space variables of this quantity. And then leveraging that, one can go one step further and define a generating functional for the connected correlation functions of the NNFT. This is another term for connected correlation functions. So this is a direct correlation with the statistical moments obtained as ensemble averages. These are the statistical moments obtained as ensemble averages, where you do not need to know anything about what the action is, what the field theory looks like, nothing. You just can generate the outputs and you can get this. Or if you don't have a way to generate the outputs, you can then write down the correlation functions as integrals over the weights bias, their distributions, and the outputs in terms of the weights bias, post-activation, etc. Now, we are going to now keep things short and just throw in this terminology. This is a method from statistics called Edgeworth method. And after going through a bunch of steps, this shows that the NNFT field density, which is e to the power minus action, because it's Euclidean action, that takes an expression in terms of these connected correlators from the architecture space. So these are for, here I have kept things pretty schematic. So these are connected correlators when xi's are random variables. So you have to promote them to random valid functions. Then you get the corresponding expression for the NNFT density. And the connected correlation functions of the field phi in the usual case can be obtained from the cumulant generating functional by this mathematical definition over here. In a nutshell, the 3 pages that I showed you combines into this. It's a method to generate the partition function of the dual field theory, starting from the connected correlation functions evaluated using statistical moments in terms of the architecture space variables. So the starting point does not have any knowledge of field theory, but then we leverage this Edgeworth method and eventually infer the action of the dual field theory side. And in fact, that Edgeworth method can give you this this kind of a form for any dual field theories, both non-perturbative as well as perturbative. So even if the action has a very complicated structure, it is possible to write down that structure in terms of this kind of expression. And I'll explain why that is the case. So first, the free action, in fact, this can be always derived analytically if we know the initialization information, because this only involves a single operator, which is the inverse of the kernel of the neural network output. So the kernel is the two-point function of the neural network output ensemble. And there are nice analytical ways to evaluate them, get closed form expressions. And from those closed form expressions, one can get a closed form expression for the free part of the action. And this neural network kernel actually does not change whether you valid central limit theorem or not. By that, I mean the neural network kernel itself is invariant if you change the weight of the architecture. However, if you change the parameter distributions, this is going to change. So let me edit what I just said 2 sentences back. This does change when the parameter distributions change. So suppose you start training an architecture, then the parameter distributions are going to evolve with time. So the two-point function of the architecture is going to evolve with time. So the free action is also going to change. However, if you just take a neural network architecture and a neural network architecture initialization and don't change anything about the parameter distributions, but just keep tweaking the weight of the hidden layers, then nothing changes in the free part of the action. That's the subtlety. Now, there is also an interacting part, and this interacting part includes an infinite number of terms. So that is the thing. So this is the reason you can represent any dual field theory, which is weakly interacting or non-perturbative, all of them in terms of this inverse way to infer the action of the NNFT. So this contains an infinite number of terms, and realistically, it is not possible for any human to compute all these infinite number of terms, and we need to have some notion on when we can truncate computing these terms. So for that, we set up a new set of Feynman rules, which gives us an answer to both on how to infer the couplings and when to truncate these. To compute the couplings, we get some Feynman diagrams involving the connected correlators, which are evaluated in the architecture space. So the connected correlators from the architecture space act as the internal vertices in these new Feynman rules. And then one can show that when we are violating the CLT by finite weight while keeping IID parameter distributions, these have a clear scaling. So some of the diagrams and their combinations will have 1/n scaling leverage over other diagrams and their combinations. So this acts as an order parameter. Each of the diagrams provides some kind of a scaling associated with 1/n, and taking advantage of those, one can then say that, going back here, one can then say that some of these couplings will have a more relevant scaling in 1/n as compared to others. So suppose we are flowing towards large N, we will be able to see which are the couplings that would become irrelevant with large N faster than others. That tells us that these are the more relevant interaction terms as compared to others. And because of these, if we want to keep the first 3 leading order correlations, these are what we should keep. Just to summarize, if R is lesser, then those are going to be more relevant terms if we go towards large N limit. Now, if we violate the central limit theorem, both by finite weight as well as non-IID parameters, then the connected correlation functions, which are the internal vertices, they have mixed n scalings, and then we don't have a clear notion on how many terms we should keep in the sum. So then things get very tricky. So this is a snippet of the new Feynman rules. just an example. So for generic architectures, when we have finite n effects giving us interactions, the first leading order contribution comes because of the connected 4-point function that varies as 1 over n. Here is the diagram. And the rest of the terms go as 1 over n squared. And the action at leading order in 1 over n then would have a free term, then this, and then 1 over n squared. Now, in terms of a real-life architecture, we took this simple cosine activation function and some IIT parameter distributions. And here, this is the free action, and this is the 1 over n leading order quadratic interaction, and then there is 1 over n squared. And this is the summary. So the NN architectures coming from the machine learning community gives us a library of field theories. So suppose you want to take advantage of different kind of statistical field theories for some particular problem, then this is the way to do it. You can take any architecture out there. You can find out what the corresponding action is, and then you can also train the architecture because training up the parameters, and then the action will change in response to the training updates to the parameters, and one can still compute what the actions look like as you keep training. So even during training, you can trace out how the actions are evolving. So it is some kind of a flow that's not RG flow. I'm not discussing that, but training, in fact, gives rise to a flow in the NNFT space, which is different from RG flow. So in a nutshell, this is the duality, and we have just discussed one-sided direction from architectures to actions, and then I would discuss the rest of the stuff, but I will take questions and drink some water while we do that.
Yeah, Anindita, I can't resist myself asking that, let's say I want to solve the lambda 5-4 textbook problem. How will I set up the training data in this case?
So we have not trained to solve 5-4. I'm going to answer how we solve 5-4 in this particular method. We solve 5-4 at initialization. So there is no training. And it also answers, so the question you asked is related to the previous question you asked on how we can get some operator like a phi cube or phi square term and insert that.
So Shobhoshachi has a question.
Hi, a naive question is how does this Edgeworth expansion that you talked about work when you have infinite number of terms in the expansion of the action?
That's a very good question. Sorry, I didn't have much time to discuss this part. So the answer in a nutshell is that we have found out that depending on how you are violating the CLT, there is a clear prescription on the scaling between the connected correlation functions, or a clear prescription that there is no such scaling between connected correlators. That's the thing. Can you please repeat the rest of the question?
Yeah. I mean, when you have the way you are using the Edgeworth expansion, and you have connected correlations in the, let's say, exponential minus s, you have an infinite set of expansions. So how do you use the Edgeworth expansion over there?
Oh, yeah, right. So practically, it depends on how you're violating. So suppose you're violating just by finite weight, then 1 over n is your scaling parameter. You will get the leading order term, which is quadratic. So the free action does not have 1 over n dependence, but the quadratic has 1 over n dependence. The sextic has 1 over n squared dependence. If you have cubic, those will have 1 over square root of n dependence. Now it depends on how large n is. Suppose n is 1000. Then you are essentially getting a quadratic interaction that has a 1 over 1000 factor, and the sextic has 1 over 10 to the power 6 prefactor, right? So you can, just by studying what the value of n is, then you can rule out some of the interactions that are irrelevant. So it really depends on what is the order of magnitude you want to preserve in the action. But the subtlety is if you are violating the central lemma theorem with also non-IIT parameter distribution, then you will have to check for each of the, going back here, for each of the couplings, you will have to check what the associated 1 over n scaling is, because there is no clear prescription in that case.
And
All
one
right.
more quick question, if I may. So what happens when I introduce interactions and which might introduce non-localities in the theory?
Yeah, that's also related to the question that Sanmay has been asking. So let me go ahead.
Yeah.
I have 7 minutes, but there were many questions.
Sure. Okay, sorry.
So no worries. Let me answer this part in details, and I'll have to skip the fourth section. So this is from action to initialized NNs. And action will mean that we may have these operators with phi cube term or phi square term, or we might want to have this simple textbook example of phi 4 theory, and we want to know how we can get an architecture where the output ensembles would represent that action when there are asymptotically large number of outputs in that ensemble. So that's the question. How do we formulate this? How do we set up a set of rules so that given any action, we will get a corresponding architecture? So here is the prescription. First, we have to make sure that whatever theory we are trying to get this way, the action can be written as a free part, and then the rest of the terms can be written up as operators. So this can be more than one operators. For simplicity, I will discuss how you can just insert one operator in the action of NNFT. Now let's go ahead. So this is a two-step process. First, you have to get an architecture corresponding to the free action. So for that, what we do is this. First, we have to get an infinite width. So why infinite width? That's a good question. So that we want a free action. And for free action, we need an architecture that obeys central limit theorem, which means infinite width hidden layers and IIT parameter distributions. So you have to choose the width of the hidden layers as IIT, and then you have to also cleverly choose the parameter distributions. So you have to actually observe what the free action looks like and infer what the inverse propagator looks like. Because the inverse propagator of this field theory should match with inverse kernel of the architecture. And to that end, you have to also intelligently guess how many hidden layers should be there and how many activation functions should be there. It sounds a little difficult, but if you play with architectures a little bit, you get a hang of it. Now, the way NNFT works is once you get this, the interaction does not change the free part of the action. And this happens because here we are trying to first initialize the free part and then trying to just insert the interaction. And the inverse propagator itself will not change in response to that. I don't have more time to explain this, but I'm happy to discuss this afterwards as well. So the step 2 is that we have to deform the parameter distribution of this architecture. Deforming the parameter distribution deforms the architecture itself, and in response, the field theory partition function also gets deformed, and that deformation inserts the interaction in the field theory action. So the way we deform the architecture is by redefining a parameter distribution. This was the initial IID parameter distribution. G is for Gaussian because it corresponded to a free action, which is associated with the Gaussian distribution over phi. But now we are talking about deforming this architecture to something that has this new parameter distribution where there is a term in the exponent. This is an operator of phi, and phi depends on all of these parameters collectively denoted as h. So this depends on the choice of weights, bias, activation functions, hidden layers, depth, everything. So because of that, all these parameters in this probability density of all these parameters in this particular probability density now will get statistically correlated with each other. So we are breaking IIT in a nice engineered manner. And this will insert this particular term in the NNFT action via the partition function, because the partition functions are identical both for the architecture and for that field theory. So this is the nutshell. First, you have to get an architecture that gives you the free action, and then you have to deform the parameter distribution by combining the free IIT parameter distribution with this extra exponential factor, and the exponential factor has this operator. This could be phi square, this could be phi cube. You can choose all of these x's to be identical. Then you get a local interaction term, or you can keep this as non-local as possible. This is something you can do. The only problem is that if the magnitude of this term becomes really large, then the overall contribution of this exponential would be small, and the statistical correlation between the parameters in this deformed architecture would be small. That's the only challenge. But if you can navigate around this challenge, you're happy, you're allowed to keep as many, if you are allowed to insert as many interaction terms, as many operators as you want in the NNFT action, because it shows up here. Now, as an example, I have the textbook example of lambda 5-4 theory. So this was the first step. We first had to get an architecture corresponding to this part of the action. And for that, we chose a single hidden layer infinite width architecture. Here is the details. There are hyperparameters, the mass, and this UV cutoff in the momentum space, lambda. They are hyperparameters that we choose by hand. So the RG flow in this momentum space, which will depend on the choice of lambda, that really depends on the UV cutoff that users will set here. Now, then we'll have to also insert this term in the action. So the first answer is that this is one solution to the free action. There may be other architectures out there which gives you the same free action. We have come across one solution, but nothing guarantees this is the one and only solution. That's something to be kept in mind. And then starting from this, we take the IIT parameter distributions over A, B, and C. And then here we have this local quartic interaction term. So this lambda is something that here this is something we need to choose as a number, because ideally when you are getting a parameter distribution, you need to specify the details like the means and the covariance of the parameter distributions, right? So you need to specify what is sigma A and then what is lambda, and similarly this small lambda will also have to be specified. That's another subtlety. So then what happens is that you insert this particular interaction term in the NNFT partition function, you get this new interaction. And just as an ending note, because I have reached the end point of my talk, so the parameters in this case are Euclidean invariant.
Anindita, just a short interruption. You can take 5
Yeah.
more minutes since you started 5 minutes later.
All right, thank you. So I appreciate that. So here, one quick note is that this is a way to generate lambda 5-4 theory, which is on Euclidean space. But here, this is one example where the architecture can be explicitly shown to obey the OS axioms via its correlation functions. So this is an architecture which has a corresponding theory on the Lorentzian background. And this happens because you can show that all the connected correlation functions, they satisfy the reflection positivity, then Euclidean invariance, permutation invariance, and cluster decomposition. For the Euclidean invariance, we actually have to do some clever manipulation of the architecture here. So there is a theorem called symmetry via duality, which says that the action inherits global symmetry groups from the symmetry groups of the NN parameter distributions. So I'm not talking about local symmetries here, but just the global symmetries. But if you want to have Euclidean invariance, then you can choose the parameter distributions as Euclidean invariant, and the action becomes Euclidean invariant. In this manner, here we chose these parameter distributions. We chose this keeping in mind that we want them to be Euclidean invariant. This is very, very nicely satisfied. In fact, this particular choice also gives us the spatial translation. In fact, all of them combined, but specifically this. And because of all of these, we get a theory that is Euclidean invariant via this theorem, and then it satisfies the OA's axioms, and we can take this theory to the Lorentzian background. So we have this architecture. We can take this architecture to a computer. We can write this down as a code, and we can generate the outputs of this neural network. And each of the outputs, suppose we choose a collection of 20 points as inputs. And then the outputs that we will get, which would be a collection of 20 points, those would be the phi associated with this particular action. So you are drawing phi from a field density associated with this action, but those phi's are evaluated on those 20 points you have chosen as inputs. And then if you want to compute something with the field phi, then you can just take phi from there and compute something out of that. So I had a very nice diagram that I'm trying to find in a hurry here. So NNFT basically chooses a set of inputs. This can be something like a grid of points on the Euclidean space. And then the dual field theories will ensure that anytime you are generating the output of that architecture, that is a phi evaluated on these set of points. So for each of the choices of grid points, you are evaluating phi there. So you get a field configuration, and each of such field configurations are associated with the action of the dual field theory. So I'll skip Grassmann, but let me summarize this and take questions. So in a nutshell, NNFT can be free or interacting subject to the initial constraints that you put on the architecture. How you define it determines how much interactions you are going to get. Then this includes a method to infer the action at leading orders for any architecture using this Edgeworth method and new set of Feynman rules. So you can generate a library of actions. And then this also includes a method to construct the architectures dual to interacting field theories via parameter deformation. So this is one case that I have presented where you have an infinite width architecture corresponding to the free action, and then you only deform the parameter distributions. But then in principle, you might also want to check whether in addition to the deformation of parameter distributions, you might also want to check what kind of interactions the finite width effects will give. And you will see that finite width effects actually give you inherently non-local interaction terms. And in this case, we wanted to get the lambda phi for local theory. So we wanted to make sure that we have a scheme that works for both local and non-local interactions. And finally, one can bootstrap the correlators of the neural network field theory as statistical moments of initialized output ensembles. No training is required in this case if you use this particular avenue where you take an interacting action and reverse engineering the architecture, then you can directly compute the neural network outputs as the field itself, field on the choice of inputs itself, and then you can compute whatever you want out of that. And the future goals, yeah, let's go on with questions. I just wanted to say there is SUSY in progress, which is based on the Grassmann work that I did not get to talk about. Now let's go ahead with questions.
So first of all, thank you. Let's take the questions. So Shobhushachi, you can go ahead.
Yeah, sorry, the host made me. The quick question is, this finite width that you talked about, does that take care of the divergences that you might have as well from lambda phi theory?
Can you explain what you mean by that? What kind of divergence you are referring to here?
It's just one loop divergences that I should get.
Oh,
or
I
there
see.
might be tree-level divergences since I don't know in this construction.
I see what you mean. So the way NNFT works, you don't actually have to worry about the one loop or tree level divergence because when you get the pre-propagator, you are getting exactly this. And in fact, if you check with finite width effects, the finite width effects do not alter this. Suppose I did not have this particular term to worry about. I only need to generate this. In fact, at finite width, you will still get this two-point function, but there will be other interaction terms. So this part does not change. That's one of the features of the NNFT, that the neural network kernel is invariant of the width of the hidden layers. Does this answer your question? So basically, you won't get rid of the UV divergences, but you will get some different interaction terms at finite width. So it's like going into two different directions in the space of all possible interaction terms.
Mm-hmm. Okay, thank you.
Mm-hmm.
So, please go ahead.
I have some few questions actually. I'm trying to understand that what kind of interactions can be dealt with this. So the O phi that you have defined, and so does that contain only up to renormalizable part? For example, if I'm working with 3+1 dimension, You are allowing up to 5.4, or you can go beyond 5.6, 5.8, those kind of interactions.
Oh, yeah, you can have this as general as possible. So the one constraint so far is that we find it a little difficult to define operators involving derivative terms. That's one of the questions I got. And if you want to involve derivative terms, you need to have a layer-like convolution. We a priori do not see any obstruction to that happening, but one has to very cleverly define this. But this can be as generic as possible. So if you're only considering polynomial interaction terms, there's no upper cap on what this can be. But if you want to have something like, and in fact, if you want to have functions like logarithm or sine that can be expanded as polynomial series in phi, that is also allowed. The only challenge would be if you contain derivative terms, then we need to see in the architecture side how to cleverly define that. So the challenge here becomes that how are you going to get derivative terms on the architecture side? That's the challenge then.
So if you have a derivative terms, and then basically the way the free part is defined, it's no more canonical in sense, right? Because you can have, let's say, for example, G2 phi.
Sorry, you are a little blurry, and
okay. So what I'm
something
saying,
after canonical did cut out. Yeah.
So what I'm saying that if you have a derivative terms in this O phi, then it may happen that your kinetic term may not be in a canonical form. Right?
No, that is not true, because see, the thing here is that the architecture determines what the free term would look like. And no matter, even if you have a derivative term, the reason we will have a derivative term is because after this architecture, we'll have some extra layers, and those extra layers will not impact what happens before that.
So let me explain why I'm saying not canonical form. For example, let's say you have a kinetic term, which is the form of polynomial like D2 phi 2, right? But you can have a derivative interaction, which is like a phi 4 D2. Now, when you combine these two terms, so basically it's like a defining a kinetic term, but now your metric is not flat in the field space, right? Because you have a 1 plus some polynomial in phi, and that is multiplied with phi D2 phi. So your kinetic term is not canonical.
I understand why you think that way, but you have to keep in mind that when we are defining the architecture itself, the input space is flat. It is flat Euclidean space. Nothing changes here. Any kind of derivative terms that we get is because, so that's one of the challenges we faced. A little digression, but this is a flat space here. Then you have an architecture which is giving you some action defined on the flat space. And any kind of deformation through a hidden layer or a convolution layer that manipulates the effects of a theory on a curved manifold will have to be, in some sense, independent of what happens here. So a priori, you may think that the term that you get here because of the effect of a curved manifold is going to change what happened before these layers, but that's not going to happen. So the thing is, the guarantee happens because of the way the neural network has been set up and the way the inputs of the neural network has been chosen.
Okay. So I have one more last question. So when you define this, the example that you are showing, so if I think of like field theory, where I have two fields of two different mass terms, like M1 square and M2 square, right? And then my free part and the interaction part, they don't commute. So I just cannot take out the interaction part, and how I deal with those kind of situations.
Sorry, I'm confused. What do you mean by they don't commute?
Because see, if I have a so M square, if you define for the phi 1, phi 2, if you define a capital phi, which is like a phi 1, phi 2, then M square is diagonal, but not degenerate. It's not proportional to identity. So in the so they don't commute with the interaction part.
No, I don't quite agree with that. I can show you one quick example. Hopefully that will explain some of the underlying concept for that. So I don't have that example, sorry. In the case of supersymmetry, we realize something so this is the Dirac example that I didn't get to talk. Here, the neural network output contains two different kind of components, and the components differ by the final layer weights. So these are different. But then when you get the action, the action contains a term made from both of these. So essentially what I'm saying, and both of these have the same mass. So essentially what I'm saying is that in the example that you have mentioned, we will have a case where, let me go back, there will be two fields, phi1 and phi2, and the neural network output would be a combination of phi1 and phi2 both. So here, mass appears here. We will have a neural network output that will have two distinct components. The first component will have M1 here, and the second component will have M2 here, such that the kinetic terms would pick up this M1 and M2 both. But then once you go into defining this interaction term, in this interaction term, M does not appear explicitly. So here, we'll have the same interaction term for both phi1 and phi2.
But my question is, can I take out that interaction term? Can I separate out the interaction part and the free part then?
In what sense? Sorry, I'm confused. So you mean
Okay, so,
you want to have a different lambda 1 and different lambda 2?
What I'm saying that, so should I deal with the full action or like S naught, which is the free part, and the S interaction, because S naught and S interaction, they don't commute. So can I just separate out it with, from the exponential, these two terms?
Yeah, it is totally up to you. So you can separate out, you can keep things together. The reason you can do this is because essentially that would be like appending two different neural networks together to make a bigger neural network. So essentially, you can also take a neural network, which is a combination of 5 different components, and separate them out into 5 independent neural networks. Those may be a combination of 5 different fields. It is always possible to do that. It really matters on what you want to do.
Okay. Okay. Thank you for the clarification.
Sure.
Okay. Maybe I will ask one last question. So, given a regular Euclidean field theory, one can approach solving using lattice gauge theories. And one can also try the methods you are developing. So just if someone has good computational resource, how do you see this neural network-based field theories are more like useful in that sense over the well-established methods?
That's a very good question. And the answer is actually very useful too, I believe. So in case of regular machine learning for field theory, there is still a first step where we have to sample a good field configuration. And for that, people generally use extra compute steps, generally using Monte Carlo. And the thing with Monte Carlo is that Monte Carlo is exact when you are doing infinite number of steps, but you have to keep doing it for a large number of steps. But with NNFT, you can bypass that sampling problem. You can in fact, so NNFT gives you an architecture where you generate the outputs on a bunch of inputs, and the output that you get is the sampled field. You have sampled one field configuration from the target theory. So this will be an alternative to MCMC. Whether this would be more useful over MCMC is not something we can guarantee yet, because I think that depends really on the kind of field theory that you have in mind. But at the end of the day, this is one of the advantages, that you are sampling a neural network output which has the interpretation of the target field itself. So here you don't, if you run into, I mean, there's very low probability that you will run into a case where you try to compute something out of this sampled field configuration, then you get very large errors. I'd be very surprised if that happens, because you are ensuring that the output will have a very nice physics-based interpretation that cuts down the chances of errors and biases. So that's the advantage. And the second thing is you can directly compute the correlation functions. So there is this notion of bootstrapping. We have checked this for correlation functions, but it may be possible to do this for other kinds of quote amplitudes as well, something we did not have the scope to explore yet. The third thing, because somebody in the audience is working on conformal field theory using machine learning, so it's not my current research topic, but my PhD advisor, Jim, is working with other collaborators to get neural networks for conformal field theory correspondence. So in that case, bootstrapping computations on conformal field theory would also become easier using this NNFT avenue.
Okay. Great, thank you. I mean, probably we will have more questions, but let's see if others have more questions. Seems not. Okay. So what we will do, Anindita, we will save the recording, and once we upload it in our YouTube, we will notify you again. But anyway, we can give a big round of applause to Anindita for this wonderful presentation and a completely new subject for us. And we at least had some idea. So thank you very much, Anindita, for accepting our invitation and giving us this seminar.
Thank you so much. I really appreciated the questions. And in future, if anybody has more questions I want to discuss, please feel free to reach out. I'm always open to discussions over emails. And I appreciate the chance to present this talk and have this wonderful Q&A session.
Great. So I will now stop the